Download this code from codegive.com, link in the description below. Backpropagation is a fundamental algorithm used for training artificial neural networks. It is a supervised learning technique that efficiently computes the gradient of the loss function with respect to the weights of the network. This allows the model to update its weights in order to minimize the error in its predictions. Key concepts of backpropagation. 1. Feed-forward pass. In this step, input data is passed through the neural network to obtain predictions. Each neuron applies a linear transformation followed by a nonlinear activation function. 2. Loss calculation. After obtaining predictions, the loss, or error, is calculated using a loss function, example mean squared error, cross-entropy. 3. Backward pass. The backpropagation algorithm computes the gradient of the loss function with respect to each weight by applying the chain rule of calculus. This gradient tells us how to change the weights to reduce the loss. 4. Weight update. Using the computed gradients, weights are updated typically using an optimization algorithm like stochastic gradient descent, SGD. Backpropagation algorithm steps. 1. Initialize weights. 2. For each training sample, perform a feed-forward pass to compute predicted output. Calculate the loss. Perform a backward pass to compute gradients. Update weights using the gradients. Code example. Below is a simple implementation of a neural network with backpropagation using NumPy. This example consists of one hidden layer and uses the sigmoid activation function. Python. Import NumPy as NP. Sigmoid activation function and its derivative. Def sigmoid, x. Return 1/1 plus np.exp, x. Def sigmoid underscore derivative, x. Return x asterisk, 1, x. Neural network class. Class simple neural network. Def underscore underscore init underscore underscore, self, input underscore size, hidden underscore size, output underscore size, learning underscore rate equals 0.1. Initialize weights. Self.input underscore size equals input underscore size. Self.hidden underscore size equals hidden underscore size. Self.output underscore size equals output underscore size. Self.learning underscore rate equals learning underscore rate. Weights initialization. Self.weights underscore input underscore hidden equals np.random.uniform, size equals input underscore size, hidden underscore size. Self.weights underscore hidden underscore output equals np.random.uniform, size equals hidden underscore size, output underscore size. Def feed forward, self, x. Calculate hidden layer activation. Self.hidden underscore layer underscore activation equals np.x, self.weights underscore input underscore hidden. Self.hidden underscore layer underscore output equals sigmoid, self.hidden underscore layer underscore activation. Calculate output layer activation. Self.output underscore layer underscore activation equals np. Self.hidden underscore layer underscore output, self.weights underscore hidden underscore output. Self.output equals sigmoid, self.output underscore layer underscore activation. Return self.output. Def backpropagation, self, x, y. Calculate the error. Error equals y, self.output. Calculate the gradient for output layer. D underscore output equals error asterisk sigmoid underscore derivative, self.output. Calculate the hidden layer's error. Error underscore hidden underscore layer equals D underscore output self.weights underscore hidden underscore output t. Calculate the gradient for hidden layer. D underscore hidden underscore layer equals error underscore hidden underscore layer asterisk sigmoid underscore derivative, self dot hidden underscore layer underscore output. Update weights. Self dot weights underscore hidden underscore output plus equals self dot hidden underscore layer underscore output dot t dot dot, d underscore output, asterisk self dot learning underscore rate. Self dot weights underscore input underscore hidden plus equals x dot t dot dot, d underscore hidden underscore layer, asterisk self dot learning underscore rate. Def train, self, x, y, epochs equals 10,000. For epoch in range, epochs. Self dot feed forward, x. Self dot backpropagation, x, y. Example usage. If underscore underscore name underscore underscore equals underscore underscore main underscore underscore. Input data set, and logic gate. X equals np dot array, 0, 0, 0, 1, 1, 0, 1, 1. Output data set. Y equals np dot array, 0, 0, 0, 1. Create the neural network. NN equals simple neural network, input underscore size equals 2, hidden underscore size equals 2, output underscore size equals 1. Train the neural network. NN.train, x, y. Test the neural network. Print, predictions after training. Print, NN.feedforward, x. Explanation of the code. 1. Initialization, we define a simple neural network class, which initializes weights for the input hidden layer and hidden output layer. 2. Feedforward, in the feedforward method, we compute the output of the network by passing inputs through the layers. 3. Backpropagation, the backpropagation method computes the error and gradients, then updates the weights accordingly. 4. Training, the train method repeatedly performs feedforward and backpropagation for a specified number of epochs. 5. Testing, after training, we can test the network's predictions. Conclusion. Backpropagation is a powerful algorithm for training neural networks by optimizing weights to minimize error in predictions. The above example illustrates the core concepts and provides a practical implementation using Python and NumPy. For more complex applications, libraries like TensorFlow or PyTorch can be used, which abstract away much of the manual work involved in building and training neural networks. What is backpropagation? Backpropagation is a supervised learning algorithm used for training artificial neural networks. It is a method for calculating the gradient of the loss function with respect to the weights of the network. By using this gradient, the network can perform optimization, commonly using gradient descent, to minimize the loss, improving the model's accuracy. Key concepts. 1. Feed-forward phase. In this phase, the input data is fed through the network, producing an output. The output is then compared to the actual target values to compute the loss, or error. 2. Loss function. This function quantifies how well the model's predictions match the target values. Common loss functions include mean squared error, MSE, for regression tasks and cross-entropy loss for classification tasks. 3. Backward phase, backpropagation. In this phase, the gradients of the loss function with respect to each weight are computed using the chain rule of calculus. This allows us to understand how much each weight contributed to the error. 4. Weight update. Once we have the gradients, we can update the weights to minimize the loss. This is typically done using gradient descent or one of its variants. Backpropagation algorithm steps. 1. Initialization. Set up the neural network architecture and initialize weights, often randomly. 2. Feedforward. Pass the input through the network to get the predicted output. 3. Compute loss, calculate the loss value comparing the predicted output and the true target. 4. Backpropagation. Calculate the gradient of the loss with respect to the output. Propagate the gradients backward through the network layer by layer, applying the chain rule to compute gradients for each layer. 5. Update weights, adjust the weights using the computed gradients and a learning rate. Code example. Below is a simplified implementation of backpropagation in Python using NumPy. This example demonstrates a simple feed-forward neural network with one hidden layer. Python. Import NumPy as NP. Activation function, sigmoid, and its derivative. Def sigmoid, x. Return 1/1 plus np.exp, x. Def sigmoid underscore derivative, x. Return x asterisk, 1, x. Input data, x, and target output, y. X equals np.array, 0, 0, 0, 1, 1, 0, 1, 1. Y equals np.array, 0, 1, 1, 0, x or problem. Setting random seed for reproducibility. np.random.seed, 42. Initialize weights. Input underscore layer underscore size equals 2. Hidden underscore layer underscore size equals 2. Output underscore layer underscore size equals 1. Weights underscore input underscore hidden equals np.random.rand, input underscore layer underscore size, hidden underscore layer underscore size. Weights underscore hidden underscore output equals np.random.rand, hidden underscore layer underscore size, output underscore layer underscore size. Learning rate. Learning underscore rate equals 0.1. Training the neural network. For epoch in range, 10,000. Feed forward. Hidden underscore layer underscore input equals np.x, weights underscore input underscore hidden. Hidden underscore layer underscore output equals sigmoid, hidden underscore layer underscore input. Output underscore layer underscore input equals np. Hidden underscore layer underscore output, weights underscore hidden underscore output. Predicted underscore output equals sigmoid, output underscore layer underscore input. Compute loss, mean squared error. Loss equals y, predicted underscore output. Backpropagation. Calculate gradients. D underscore predicted underscore output equals loss asterisk sigmoid underscore derivative, predicted underscore output. Loss underscore hidden underscore layer equals D underscore predicted underscore output dot dot, weights underscore hidden underscore output dot T. D underscore hidden underscore layer equals loss underscore hidden underscore layer asterisk sigmoid underscore derivative, hidden underscore layer underscore output. Update weights. Weights underscore hidden underscore output plus equals hidden underscore layer underscore output dot T dot dot, D underscore predicted underscore output, asterisk learning underscore rate. Weights underscore input underscore hidden plus equals X dot T dot dot, D underscore hidden underscore layer, asterisk learning underscore rate. Output the final predictions. Print, final predictions after training. Print, predicted underscore output. Explanation of the code. Activation function, we use the sigmoid function, which outputs values between 0 and 1. Its derivative is used during backpropagation to adjust weights. Data preparation, the input data X represents the X or problem, and Y is the corresponding target output. Weight initialization, we randomly initialize the weights connecting the input layer to the hidden layer and the hidden layer to the output layer. Training loop, the network is trained for a specified number of epochs, 10,000 in this case. In each iteration, The inputs are fed forward to compute the predicted outputs. The error, loss, is calculated by comparing the predicted output to the actual target. The gradients are computed using backpropagation. Weights are updated using the gradients and the learning rate. Predictions: after training, the final predictions are printed, showing how well the neural network has learned the XOR function. Conclusion: backpropagation is a fundamental algorithm in training neural networks, enabling them to learn from data. The example provided illustrates the basic principles of backpropagation, including feedforward, loss calculation, and weight updates. In practice, libraries like TensorFlow and PyTorch handle these operations more efficiently, allowing for more complex architectures and larger data sets.